Welcome Mechanics of Materials students. In this mini lecture we will be discussing one method for dealing with stress-strain relationships beyond the elastic limit. So to date we've been discussing concept of stress, concept of strain. We've introduced the coefficients of elasticity, tensile modulus, shear modulus, Poisson's ratio, bulk modulus. All of these concepts deal exclusively with material behavior down here, where stress and strain are linear. We've also noted that if we apply too much stress or we ask the material to undergo too much strain, we will depart from that elastic region and we will start deforming. We'll displace points using material mechanisms that are different from those that are elastics, and we will have irreversible deformation, and we will be in this non-linear stress-strain region, which we call plasticity. It's really easy to model stress-strain behavior in the elastic region. It's linear. It's a line. This is great. If we know the modulus and we know the strain, we know the stress, and vice versa. And we can use our Poisson's ratio and shear modulus and basically deal with any number of loading states, biaxial, triaxial. It's all good. But once we depart from that straight line, we have to have a little bit more mathematically robust way of representing the material behavior, and it really helps to know a little bit about what's going on and the direction in which we're going to depart from linear. So we're going to start with just a word about yield. We know that as we go from our elastic region up into this nonlinear plastic region, we're doing something that's a little bit energetically easier than just moving atoms off of their equilibrium positions. So one of the consequences of that is that for every bit of additional stress that we impart, the material moves a lot more. It's less stiff, so to speak. So if we were to say draw a line from the origin to someplace part way up this plastic zone between yield and maybe where it broke over here, this line is going to have a lower slope than our modulus, which represents all of our stress strain behavior in the elastic region. So the slopes would get smaller. What that's telling us is once the material yields, you get a lot more deformation for every additional stress increment that you add. It moves more. It also moves permanently, but for this, the important point to hang on to is it moves more. Okay, because we don't have a single model of behavior, of linear behavior, the way we do for elasticity, we need to create a mathematical model for what is the stress at any given strain, or what's the strain at any given stress up in that nonlinear region, mainly using test data. So we're going to do a whole bunch of uniaxial tensile tests on materials, and we're going to collect a whole bunch of points, and they're all going to be different, and we're going to try to look and see what can we say that's the same about those functions, about those plots mathematically, and see if we can't find maybe a couple of adjustable constants, adjustable parameters that we can use to tweak a single function that represents a whole lot of different materials. So that's what's known as an empirical model, and that's something that's used for lots of different applications in material science especially. One model that works particularly well for a lot of structural materials, especially metals, is something called the Ramberg-Osgood three-parameter equation. And here it is. You can look this up in any number of handbooks. So it says the strain for any given stress is equal to the stress divided by the elastic modulus. So that would be the elastic strain right here. So this first term is just the elastic strain plus some constant coefficient times your applied stress raised to a power. So this second term represents the strain that comes from stresses applied beyond yield. So the first term will capture this strain, and the other terms will capture the strain, say, if you're up here maybe, beyond that. So this is the first term, and this is the second term. So since we need to get, if we were, say we didn't already know the elastic modulus, and we were going to use this, we suspected that we could use the Ramberg-Osgood equation to represent our material, and we're trying to determine how many points we need to make a measurement at. We've got three unknowns, back to equations and unknowns. We were looking to get a value for E, for K, and for N. So we have three unknown parameters. So on any given stress strain test plot, data plot, we're going to need to make sure that we're looking at three different data points spread out. So three pieces of data to get three unknowns. And we're going to make sure they're in particular positions that maximize our understanding of the behavior of the curve. So not surprisingly, we're going to put one down here in the elastic region. That's going to give us our tensile modulus, bam, right off the bat. Then we're going to use a point that's near the maximum curvature, and this is we call this point P. So we're going to make sure that we know sigma P up here, and the strain corresponding to P, that's going to be a stress strain point that we measure, sigma P. And then we're going to get another one out here, and in some of the most useful conditions, this is our sigma Q. So we're going to get another one a little further out where the material is unequivocally acting plastically. It's definitely deforming plastically. So we're going to get a strain and stress that corresponds to Q. So basically, the further out we go, going from point 1 to point 2 to point 3, the slope of a line drawn from the origin up to the stress point on the curve is going to get lower. So our steepest curve is the actual elastic modulus. Then the slope of this curve going from the origin to point 2 at sigma P is going to be less. And if we ratio the slope of this line to the slope of the modulus, we could say it's the modulus times some coefficient P. And the same thing with Q. So you've got a stress strain slope of E in the elastic, an origin to the curve line slope of PE to point 2, and then QE to point 3. As it turns out, if you collect enough empirical data, you'll find that if that value P and the value Q, that you're going to multiply by E to get the decreased slopes of those lines leading from the origin up to points, P and Q, or points 2 and 3 here, times modulus. If those are 0.8 and 0.7 respectively, then we're going to fairly accurately represent room temperature behavior of metals that have a defined yield point, which is a whole lot of things people work with for any kind of structural component, not just highways and bridges, but a lot of small mechanical components. These are ductile metals. They have good fracture toughness generally. They're fairly easy to machine. They're fairly cheap. They're recyclable. So they're things you're going to use. So if we zero in on application of the Ramberg-Osgood, call it model of elastic and plastic behavior, and we say, okay, we're only going to look at things that have a P of 0.85 and a Q of 0.7, then we can rewrite this basic expression here to something that is appropriate only for those two P and Q values. And it turns out now we can rewrite it and say strain at any point is the stress that you've applied at that point divided by our modulus times this expression. Now it looks like we got more complicated, but as it turns out, we've now defined those constants. So we end up with 1 plus 3/7 Then we multiply by, again, our applied stress, and that's the same applied stress you had out here, divided by the stress that corresponds to 0.7. So that's this measured stress. So these are all coming from a measured test. And you're going to raise that to a power of n minus 1. N, as it turns out, I bet you were wondering where you're going to use that sigma p. You're going to use it down here. N is 1 times the natural log of 17 over 7 divided by the natural log of the ratio of the stress that corresponds to point Q divided by the stress that corresponds to point P. So that's the 0.7 and 0.8 values. So this stress divided by that stress. So that's going to be a positive value. We can calculate the natural. The natural log is defined. It's positive, but it's going to be less than 1 because the slope is smaller. Okay. There is something special about a Q value of 0.7 for this type of material, and as it turns out, a Q of 0.7, if you take a look at it, if you were to, instead of dropping a line straight down to the x-axis and saying, hey, here's the stress that went along with, or the strain that went along with that stress, if we drew a line parallel to E and dropped it down, that's parallel to E, right over here. So if these two were parallel, we would find that we hit the x-axis at 0.2%. So that's the classic 0.2% offset yield. That is very, very convenient because that value is well characterized for a lot of materials. So that gives us an extra check that our test data is doesn't have a problem. So we're working with a well-known characteristic of the material, a tested quantity. Okay, so our N, which ends up being the same as one of our big parameters in the general Ramberg-Osgood for these situations where P is 0.8 and Q is 0.7, or the stress, so stress at Q is the 0.2% offset yield. N is going to be the 1 plus natural log of 17 over 7 divided by natural log of the stress at point Q divided by the stress at point P. And we can use that in this kind of specialized application of Ramberg-Osgood that applies when P and Q have these respective values, which turns out to be for the case for a lot of materials. Once you've got an expression for N and an expression for E, which you can measure right off of your test plot, then you will know strain for any given stress, including those beyond the yield. So this gives you a way of basically relating stress and strain beyond the yield point. So if you think about what's happening after yield, a phenomena that's occurring is something called work hardening. So things are changing in the microstructure that with each increment of strain, it typically becomes a little bit harder to get the material to strain. So we need a little bit more stress to get it to move a little bit more. So that ratio of a little bit more stress needed to achieve that additional increment of strain is known as work hardening. And it's one of the easiest ways to strengthen a material. Granted, it does come with a price and fracture toughness reduction, but knowing how much additional stress we get for each increment of strain in that plastic regime is part of what this model is giving us, and it's contained within that N. So we can use that relationship and some given test data to get an idea of, at least a general idea of what's going on in the plastic region. We won't be delving into that too much in this course. We will mainly be sticking to elastic design and then checking to make sure we haven't yielded. But just so you know, there are a few selected applications, especially things like forming, where you want things to yield, where understanding something about that stress-strain relationship beyond the yield point is very important. Couple of general cases, like we've said, when we define Q as that 0.2% offset yield, we're now able to model a little bit plastic stress strain for really common materials. One thing to note, if N gets very, very, very big, and we have an infinity basically for N, we end up getting a situation where the additional stress with increasing strain in this plastic area is zero. And so we end up getting a stress strain curve that plots something like this. We go up with our elastic behavior, we hit the yield point and then flatten out. So it's like we don't need to apply any additional stress practically to just get the material to strain like crazy. And this is known as elastic perfectly plastic behavior, where we basically have a flat line stress strain beyond the yield. And so that's something that doesn't work harden at all. It just keeps going. You can smear it along with very little additional stress to get more strain. And there are certain materials that will exhibit that, and that's important to know if you need to get something to move. It might have some consequences if we are designing against yield and maybe we don't calculate things right. Knowing something that won't work hard, knowing that we've made something from a material that won't work hard means we'll get a lot of strain if we don't keep things in the elastic regime. So that's something important to know about the consequences of maybe not designing properly. But of course, we will be using safety factors and keeping things in the elastic regime when we want them to avoid that. So this is mainly a consideration if you ever need to worry about forming materials, so getting the shape you wanted in the first place. So that is it for our discussion of nonlinear stress strain. Again, we're not going to do much designing around this in this class. If you take a materials processing course, this will be something that you will definitely be looking at again in terms of how much energy, how much force you need to shape something or change something. But you'll have a few simple exercises where you can apply our 0.2% yield Q, sigma Q, Ramberg-Osgood model. And beyond that, you'll be sticking mostly to the elastic region.